Okay, welcome. So today's session is going to talk about planning and learning and hopefully how the two are similar so that it sort of unifies the different techniques that we've talked about in previous weeks. So for these sessions, they're not terribly formal, so feel free at any point to just unmute, ask the questions, let me know if I'm going too fast, too slow, and also if you can't or don't want to unmute your microphone, you can just type something in the chat. I will do my best to monitor that as we go. All right, so we're going to do a quick recap on the basics in terms of how we're formulating our RL problems, and then specifically get into planning, how that's distinct from learning in the RL lingo. And we'll talk about this general Dyna architecture, talk about heuristic and Monte Carlo tree search, and then a little bit time at the end just to wrap up and connect all the different ideas that we've talked about so far. So quick recap, in reinforcement learning, we have three key concepts. We've got an agent, it's operating in an environment. Typically, the environment's uncertain. You don't know everything about it. And the only signal that the agent is getting is a scalar reward signal. So it's a number, a positive or negative number. It's not getting a whole lot of information. We're trying to maximize not the short-term reward we get for each action, but rather the long-term return over all of time. So that's how we've modeled things. And it turns out that there are lots and lots of problems you can easily model this way. What we do is we use Markov decision processes. And so in this Markov process, we have a series of states, and we assume that for every state, it doesn't matter how you got there. All you need to know at a given state is the fact that you are in that particular state. I'm in state 11, and I don't need to know how long it's been or where I was previously. I just need to know if I'm in state 11. That's everything I need to know about my current situation. So it turns out that pretty much any, I don't know if any, but some would argue any problem can be formulated in this way. The tricky thing, though, is that the more information you need, then the number of states explodes. It grows very quickly. And so that becomes problematic. If you look at the methods, we're just showing simple examples for small problems where then you can enumerate the number of states. So a lot of these, it's like, hey, here's a sample grid world problem. The grid is, 10 by 20, so there's only 200, positions. There's only 200 states. Backgammon, it's 10 to the 20th, and then, self-driving car, I don't even know exactly, how you enumerate that. So with these Markov decision processes, sometimes for me, it's easier to view them as a graph. So the big circles, are states, and then you can take actions, which would be represented here by the little dark circles. And then the edges show the path that you would take. It could be deterministic, where when you take an action, you always wind up in a particular state. It could be stochastic, where you take an action and there's a certain probability you wind up in one state, a different probability you wind up in other states. So that's how we're formulating these problems. And the notation we have, the key things here are, if we have a value function estimating the total return, again, not the single step reward, but the long-term return, we use V to represent that value function, and we use Q when it's the value for a particular state action pair. So we talked about the Bellman equations, and this basically says that the value at a given state is just the sum of all the actions you can take, and then all the states that you might wind up in next from those actions. And it's a sum of the immediate reward and potentially discounted. Gamma could be equal to 1 if it's not discounted, but discounted return from your successor state. So this is a recursive formulation. We can say that this is the value in a given state. We can also say, if you found an optimal policy, what must also be true? What must also be true is that basically, if you find the maximum of all the different options, then that must equal your value. And the same thing can be said when we do state action pairs, when we do the Q function, that basically the value of a given state must be basically the max of all the places you can wind up and all the actions you can take later. And we utilize these recursive formulations in a number of the algorithms we talked about before. So we do this form of policy iteration where we evaluate and try to find for the current policy, what is the value of all the different states? And then we can do improvements where we try to tweak the policy to make it slightly better, and then we can alternate and we can repeat. And so this idea of generalized policy iteration we've talked about for many of the different algorithms, where essentially you're doing some amount of tweaking the policy, which actions you're going to take, and you're doing some amount of improving your estimate of the value function, but you're not necessarily doing it for everything. So you can do it for certain things, and then there are theorems that say basically if you did this infinitely long as you do this infinitely, that you touch all of the different states and actions eventually, then this whole thing will converge to optimality. So from that, we still have challenges, and in particular, you have to decide how you're going to formulate your problem, how you're going to do your reward design. You have to figure out how you assign credit. So if you have a good or a bad outcome, which of the multiple actions you took. And we have to balance exploration and exploitation. So these are things that we deal with, and ultimately, we're going to deal with memory and compute limitations. And in the more advanced algorithms, which we haven't really touched on too much, it's really about getting the models to converge quickly. So convergence may be fine theoretically if you did this infinitely long, but we don't have infinite long for the problems in the real world. So two algorithms we talked about that are going to we're going to circle back on. We talked about Monte Carlo. And so in this case, what we do is we simulate entire trajectories from beginning to end, and we say what was the actual return from those trajectories. And if you do enough of these, then you get a pretty decent estimate. We also talked about temporal difference learning and the Q-learning algorithm, which really just does an update based on here's a state. When you take an action, what's the next state that you wind up in? And so it's a very small update, whereas Monte Carlo is if it's an episodic task, you just play it out all the way to the end. Here, it's just boom, it's just one step. So those are some of the things that we've talked about. And so now what we're going to do is we're going to get into planning, distinct from some of these algorithms. So what's the difference between planning and learning? So to talk about the difference, what we really need to talk about is what are models, specifically in the reinforcement learning context. So the term model is what we talk about where if you're in a given state and you take a particular action, that tells you what the reward and what the next state will be. So you can have a deterministic type of environment where 100% of the time when you take a particular action, you know exactly what state you're going to wind up in. So something like chess, for example. When you say, I'm going to move my piece here, then the next state is the next board position after you've moved that piece. So there's no stochasticity, but many situations obviously have some variability in where you're going to wind up. And if that's the case, then what you can do is in your model, you can do one of two things. You can have a distributional model where basically you're tracking a probability distribution. So in poker, if you get dealt two cards, there's 52 cards in a deck. So 52 times 51, roughly 2,500 different possibilities for what cards you could get. And if you're thinking about them in certain ways, then there's more than one way in which you could get, for example, a pair of aces, because there's 4 different aces in the deck. And so there's different ways in which you could get 2 aces. So that would be a distributional model. Another thing you can do, which is often much, much simpler, is a sample model, where basically you are generating samples. So you obviously have some information that you know about the environment, but just in terms of procedurally, it is often much simpler to do samples. So, a complex thing would be like if you're trying to do a self-driving car, you may not know the exact probabilities of all the different things that could happen, a car swerving, of a pedestrian or whatever, but it's easy enough for you to just produce, samples where sometimes this happens, sometimes that happens. Even simpler, if I said to you something like, um, we're going to roll, a set of dice, and uh, we want to model what the sum of all the different dice is. Except in this case, I'm going to give you, um, I've played Dungeons and Dragons in the past, so you have all these different dice with different numbers of sides. So if I said you're going to roll one 20-sided die and two regular 6-sided dice and one 12-sided die, and I want you to give me what's the distribution of the different sums. I mean, I can do it, but it's definitely not trivial. Whereas actually just creating samples would be pretty easy because you just do random number generator. You say random 1 to 20, random 1 to, I don't remember what I said, 1 to 6, 1 to 6, 1 to 12. And it's pretty easy for you to then just add those numbers together. So you won't necessarily know exactly what the probability distribution is, but your examples will actually follow that distribution. The other issue is that even if you had a decent distribution, if you do that for one step, that's one thing. But you go 2 steps, 3 steps, and those probability distributions can grow very large and very complex very quickly. So that's the problem that people have had with poker, is that they may be able to say, I know the exact probability that this particular card would come next, but keeping track of all the different probabilities as you go through a poker game can actually get pretty enormous very quickly. All right. So when we talked about temporal difference in Monte Carlo, we did not require a model. We just needed sample experience from the environment. And so those are called model-free methods, and the term we use for those is learning. So what we're going to talk about today that's a little different is what is planning. So we talked about dynamic programming a little while back, and in dynamic programming, we assumed that we had a perfect model of the entire environment. And what we did is from any given state, we would look at all the possibilities of the different actions and the different successor states you could wind up in, and all the different probabilities of those. And then based on all the successor state values, we could then back that up by doing a weighted sum of all the different probabilities, do a weighted sum of those values, and then we could update the value for our current state. And if we swept through all the different states and we did this, and then we repeated over and over again, then eventually this would converge asymptotically to an accurate value for any given policy pi. So that was actually a form of planning. We didn't really call it planning. But there's more that we can do that doesn't have all the requirements that dynamic programming did. We don't necessarily have to have a perfect model of the environment. Rather, what we're talking about now is keeping track of an estimated model of the environment and trying to improve that model over time. And so that is where planning comes in. So planning formally is a process where it's given a model, and ultimately what it does is it helps you select the action. It helps improve your policy. So what's different about having a model from the algorithms we looked at before, like TD, Q-learning, is that now if you're in a given starting state and you're taking an action, not only can we really follow an action and get a signal back from the environment, we get an actual reward signal and it tells us what our new state is. But with our model, we can say, this is what we think would happen if we took a particular action. And so essentially what we can do now is we can simulate experience. And so again, if you have a distributional model, then basically you would be seeing a set of probabilities of all the places you could wind up. But if you're doing a sample model, then essentially you can just do simulated trajectories through your environment. And so ultimately what we're talking about is how can simulation be complementary with actual real life experience with the environment. All right, let me pause here. That was the whole big reinforcement learning intro recap, and then the planning intro. So let me just pause here and just see if there's any questions so far. You guys with me? All right. Question?
Oh, no, just saying so far so good.
Okay, thanks. Appreciate it. So in the Sutton Barto book, really talking about state space planning. So this means that you're going to have a value function, and we're going to search the state space, and we're looking for better policies. And overall, you see it has these steps. So you start with your model. You're going to simulate experience. Now, this experience may not be 100% accurate because now we're talking about this is an estimated model. But from this experience, we're going to get rewards and returns, and we're going to back up those values to improve our value function, and ultimately, with our improved value function, to improve our policy. So if you think about dynamic programming, it followed this structure. The simulated experience that it did was really only one step. It said from this action, what are all of the next things that you could wind up in? It wasn't going deep, it was just going one step. And then in the case of when we talked about dynamic programming, we assumed that we had a perfect model. And so if that's the case, then your simulated experience is actually perfect. And so if that's the case, then when you do this and you repeat until convergence, then these values are going to be completely accurate values for a given policy in that environment. We're now going to also generalize this to the case where we are keeping track of a model. And so then this estimated model gives us estimated experience. And so this will improve over time, but this is not, once again, this is not perfect. So one of the things we can do now is we can say dynamic programming, that was that theoretical case. What's a real case? So the very, very simple form of it is we can take our Q-learning algorithm. So in our TD world, we simply are in a state, we take one action, we wind up in a new state, and we use the information from that new state to back up one and update the value of the previous state. Really, the value of the previous state action pair typically. So all we have to do is take that process, but instead of saying we had a state, we took a real action and got a real reward and next state from the environment, we can do a simulated action, and what our model tells us it predicts will be the reward and the next state. So in this algorithm, basically, you select, again here, states and actions, in this case at random. We send that to our model to obtain what the model predicts is the reward and the next state. And then this update is the exact same update that we did in Q-learning, okay? We say that our estimated value for this state action pair, we're going to update it by a small value alpha times the reward plus the discounted return minus what we thought it was. So the delta between what we think the reward plus discounted return is and what our previous estimate was. So this is the exact same formula that we used in our Q-learning algorithm. The only difference here is, again, instead of actually online, on policy, interacting with the environment, we're using simulation. And so what we'll see next is that we can actually get even more sophisticated than just simply doing one step. So now talking a little bit about if we were to integrate that, how would we integrate that Q planning step into the real world? So if we do our planning online, okay, so dynamic programming, we talked about that as being like a theoretical thing you can do. You don't even need to be in the environment. You have a perfect model, and so then you can just calculate everything in advance without even ever setting foot in the environment. But in this case, if you're actually the agent and you're in the environment, so you imagine you're playing a game or you're a robot, you're interacting with the environment, then as soon as you take an action and you get some experience, so that interaction gives you, the reward in the next state, there's two things you can do with it. That information can help you improve your estimated model of what the environment looks like. And then it can also do all the learning that we've talked about before, whether it's TD or whatever algorithm. We can do both of those things. Excuse me. So in the diagram, you can see that this sort of short path here is what we've been talking about up till now, where once we get that experience, we update our value function and ultimately update our policy. But the other thing we can do is we can use all of that experience to help build us a better, over time, more and more accurate model. And then we can run simulations against that model, which also help us improve our value function. And the thing is, the reason why planning is very useful is that planning tends to be, excuse me, much more sample efficient in terms of the actual interactions with your environment. So we have an algorithm that's in the book. This is the DynaQ algorithm. This is a very simple. So this is not getting complicated yet, but this shows how we can integrate learning, direct RL, with planning. And so in the DynaQ algorithm, which I'll show on the next slide, excuse me here, we're going to use the same TD Q-learning algorithm that we know to do our direct reinforcement learning. Excuse me. And once again, this only requires just one step, one action. The planning that we're going to do is the simple Q planning algorithm that we talked about. Again, it's just comparing one state in action to the next state in action that we get. And in the case of the basic DynaQ algorithm, model learning, it's not really learning, basically. It's just very simply going to assume that the world is deterministic, even if it knows it's not. And it's just going to track, hey, for every state in action, the last time I did it, what was the reward and what was the next state? So each time it does it, it just overwrites and it assumes that that is, the one and only value. So obviously that's not necessarily true, but over time, even if it's not true, over time, it will, flip to different values and it'll average out kind of over time. And then finally, in this diagram on the right, you can see that you're having experience here. And when you get experience, TD learning, whatever these direct RL methods, they're going to update our value in our policy. That's one path. The other thing we're going to do is we're going to improve our model. And after we improve our model, we can do planning. But there's one other element here that we haven't really talked about up until now, which is this search control idea. And so this is the idea of, if we're going to do simulations, what should we actually simulate? Which states and which actions? So we're not really going to go, we're not going to talk about this in too much detail yet. That comes as we basically improve upon our basic algorithms. So here's the pseudocode for our basic DynaQ algorithm. And again, we're doing this in a tabular world where we assume we've got a small number of states, and we're just keeping track of the value function for all state action pairs. Um, so for this algorithm, what we're going to do is we're going to pick our state. Our action we're going to pick using an epsilon greedy policy. So this means that we will always do a little bit of exploring. Okay, so we won't get stuck in a rut where we're always just picking what we think is the best action. A certain epsilon percent of the time, we'll take a random action. Once we take that action, this is really step C here is really taking the action. The environment gives us the reward and the next state. So what we do with that is we do our regular TD learning step here. This is our TD update, where we basically just simply say that alpha times a small amount of the difference between what we got and what we thought we were going to get. Step E here, this is where we're just simply overwriting the model. And so for that state in action, we're going to assume that we always get this reward and we wind up in this new state. Then here's the planning part. So we're going to repeat n times where we pick a random state in action, and from that, we're going to ask the model, what do you think is the new state in action that the reward and new state that we're going to wind up in if we start in this state and we take this action. And we're going to do our Q planning update. Again, same algorithm here. So this Dyna algorithm is meant to be really simple. It's not particularly smart. And in particular, what you'll see here, the search control is just random. So what it's saying is we're following our policy in terms of interacting with the environment, but when we do planning, we're just randomly updating all sorts of different state action pairs without much intelligence. So this will change in the next couple slides as we talk about different things we can do. All right, let me pause here. Any questions about this DynaQ algorithm? So again, if we had just stopped at step D, this would have been Q learning. But instead of just doing regular Q learning, then we add a step where we do a learning and then we do planning. Any questions? Okay. So on the previous slide, what it showed at the bottom for planning is that we're going to do n planning steps for each time that we take one action that we interact with the environment. And so if we're doing things online, this is often a realistic assumption. So if you think about like, the computers that have played, backgammon, chess, Go, in the time between your moves, the computer can actually do quite a bit of work in terms of quite a bit of planning and thinking. And so in the book, there's an example here of a grid world. It's sort of like a maze. There's a few obstacles. And so if you start here at S and G is your goal, then when you don't do any planning, if you just do Q learning, then it's going to wander around all sorts of, let's say you initialize it with just a random policy where 25% whether you go up, down, left, or right. It's going to wander around and wander around and wander around, and most likely after hundreds, if not thousands of steps, it's going to randomly luck into this part of the grid, go up one and then up two, and actually make it to the goal. So if the rewards are 0 for all actions, except when you get to the goal, you get a reward of +1, then the TD update is going to basically say, okay, I'm going to do an update of if you're in this state here on the second row on the far right, then going up, instead of having a value of 0, actually has a value of something. It's going to be alpha times, whatever. So it's going to be a positive number, whereas all our other values initialize 0. This one now has a positive, and so the greedy algorithm is going to tell you from this state you should go up. But the reality is that the basic Q-learning algorithm is only going to update this one state. It's not going to update anything else. And so what they show is an example where if your n was 50, and after that last interaction here, you do 50 planning steps, then in this case it's random. This is still the random Dyna Q. So it's random which states that it's going to update. But in this case, it might randomly at some point hit this state and say, oh, well, left may be 0, right may be 0, down may be 0, but this one up here has a non-zero value. And so if I go up, then I'm going to also have a non-zero. It might be a little smaller than that one, but it's still going to be non-zero. And then eventually you might touch this one and these, and so it shows that with n equals 50, you're not necessarily going to update the value on 50 states, but on a certain number of them, you're going to randomly stumble into them and you're going to update those. And so you can see that, possibly with, in the case of no planning, it might take you, I don't know, dozens of episodes before you finally sort of flesh out the value function for all these different states. With planning equals, with 50 iterations of planning, you might in just 2, 3 episodes, you might actually have estimates for all of the different states here. So that's when we say it's more sample efficient. It's much, much faster. And so that's really the value of adding planning to learning. And so we're not really getting rid of learning, we're not substituting it, but we are basically using the two as complementary processes. All right, let me just pause for a moment again. Any questions? All right, so what we showed here was a sort of a basic algorithm. And so if you use the DynaQ algorithm that we were looking at, initially you have missing values for your value function. You don't know. And if you're using an epsilon greedy policy, it will walk around, it'll stumble around, and it'll eventually, it'll update those values. And it'll do a pretty decent job of that. What the DynaQ algorithm won't deal with well is if your environment actually changes. So if you're not in a static environment, but things are moving around, then the value of a particular state might be different over time. So the book shows there's this DynaQ Plus, and what it does is it keeps track of how long has it been since you actually interacted with the environment for each state action pair. Okay, we're not talking about the simulations. We're talking about actually really interacted with the environment. And what it does is it applies a bonus that increases over time. What they show in the book is it increases with the square root of the number of steps. But this bonus is added to the simulation, which then increases the estimated value for state action pairs that you haven't tried in a really long time. And so that essentially then incentivizes it will make the model then eventually try things that you haven't tried in a long time. And assuming nothing's changed and they actually still have a very low value, then as soon as you try it, your time resets to 0, and then the reward value, will still be low, and so then it won't actually go there again. But if it finds a new thing that now has a high value, it can update. So basically, this DynaQ Plus does more exploring than DynaQ. There's another optimization we can do called prioritize sweeping. And prioritize sweeping, if we go back to the previous slide, we said we're going to do 50 random updates here. And we just stumbled upon that, you know, this state had a non-zero value. And at some point, we picked this state. And so then we, when we ran an update on this, we updated it. Instead of just randomly picking states, what we can do is we can keep track of which states actually had their values updated. And if that's the case, then the states that lead into it are the ones that are most likely going to get updated next. And so rather than doing things randomly, you can imagine just sort of like working backwards in sort of a increasing wave front from any place that's updated. So it's a little bit tricky to implement this, but basically, you know, you use a priority queue and you keep track of things. And so, for example, once you get down to this state here, there's 3 different states that all can lead to this one. And so it's no longer just a single linear list. And so once you have 3 of these, then if I say I'm going to pick, oh, actually, sorry, we don't do diagonals. There's 2. There's 2 states that can update this. If I then pick this state over here, well, now there's another 2. And so, so then obviously, eventually, this thing, even though this thing has at most a branching level of 4, it can grow. But so there's an algorithm that basically estimates what's the order that you should do these updates. And so that's our prioritize sweeping. Another thing that we can do is, especially for large state spaces, we can do this thing called trajectory sampling. And the idea here is that you are picking the states to update in a distribution that basically matches the current policy that you're on. And how you do that is very simple. You literally just follow the policy and simulate trajectories. And so it's not just picking random single actions, but from that action, then you pick whatever new state that it winds up in, that's the one that you then update next. And then you do this until you get to the end of an episode. And so if you do this, then what happens is it focuses the updates towards the states that you are likely to actually encounter based on your current policy. So as your policy gets to be, you know, a little better than random, it's focusing attention away from the bad states, and it's focusing attention on the states that you think might be good, and then over time it really focuses. So there's some charts in the book that show that basically if you do this, if you do trajectory sampling and you follow the on-policy distribution, it accelerates learning early by a lot. It really keeps updates on the states that are promising, the ones that have, you know, better value estimates. The curves also show that in the long run, trajectory sampling falls behind. So it might focus too much on just the policy that you're following. And so longer term, that's something where you may need to consider that you may not want to exclusively use trajectory sampling. All right, so let me put in another pause point here and just see if there's any questions. So this is planning, fairly simple DynaQ algorithm where we're using TD learning, Q learning, but we've thrown in every time we do a Q learning step, we also can do N planning steps. And then here are some ways to improve which N things are we going to do planning on, not necessarily just random. We good? Any questions?
Is the prioritized sweeping and the trajectory sampling, are those mutually exclusive, or can you do both of those at the same time?
I think they're somewhat exclusive. The idea of priority sweeping is that instead of randomly picking things, we have a priority queue and we keep track of which states have had the biggest value changes. And then we put at the front of the priority queue the states that lead to those, okay? The idea for trajectory sampling is that you don't just pick states one at a time. You pick a state, and then you actually, when you model it and you say what the action you would take is, you then, whatever state that winds up in, that's the next one that you update. And so you're basically uh, so instead of picking one at a time, you're actually doing a whole sequence of states by basically instead of simulating a single action, you're simulating a whole series of things.
Okay.
I'm sure there's some way to combine them, but
Yeah.
but they're
Well,
kind of
maybe you
conceptually.
would do trajectory sampling early in the process and then move to
Mhm.
prioritize sweeping sort of later in the process
Yes,
if that made more
yes,
sense.
you
Yeah.
could
Okay.
definitely do that because trajectory sampling again seems to work very well early. Because in any typical problem, you're just going to have a bunch of nonsense, things that you could do that you can, rule out fairly quickly.
Cool. Thank you.
Mhm. All right. So then moving forward a little bit on this concept of planning, we've been talking about what's called background planning. So the idea is that we're just generally improving the value function and improving our policy. What we can now talk about is focusing planning at decision time. So if you are interacting um, with the environment, rather than generally improving our policy, I can say, hey, look, I am right now in state 17, and I need to choose what action I'm going to take now. So I want to do planning in order to pick the best action. I'm not doing planning as just a general background thing to say what are, good things to do. Okay. So if we do this, we can do all the kinds of planning that we've just talked about the last few minutes, except now, instead of randomly picking start points or whatever, we're going to root all of our activity in the current state. So to be honest, this is what I think of when I think of if you're writing an artificial intelligence for playing chess, right? You're going to say, here's my current board position, and I want to do some planning on what is the best move here. At this point, I'm not trying to figure out what's the best opening. I'm not trying to figure out what's the best way to do an end game. I just want to focus all my resources on what move should I make next. So that's really what planning at decision time is. So broadly, this category of algorithms is called heuristic search. And what you do is you say, I'm in my current state, and I'm going to create a large tree of the possible continuations. Again, in my head, this is what I think of as chess AIs. I think historically, people kind of handcrafted what they thought was a fairly good policy, and then they used heuristic search to say, but we know that that's just an approximate policy. So what we want to do is we want to play things out from here and really fine tune the details of what's the next best move. And so you can imagine before we had good reinforcement learning, before we had any of the more modern things, you would just have some general idea, and from here you say I have enough computing power to compute 8 moves ahead from here, and just see what looks most promising from 8 moves ahead. And so in that scenario, historically, when they built this tree and they had values, they didn't actually store anything from the values that they got from, let's say, going a tree 8 deep. They just discarded them. So the book mentions that maybe nowadays, now that we have reinforcement learning, and instead of having a handcrafted policy, but we're learning a policy, probably makes more sense to actually try and utilize this information to update our initial value function too. So one set of heuristic search algorithms that have arisen fairly recently is what's called rollout algorithms. And I believe the people that did TD Gammon are the ones who sort of started this, where basically, if you imagine, we had Monte Carlo methods where we simulate entire episodes. In this case, what they're doing is they're simulating trajectories until they get to the end of the episode, but they're all starting from the current board position. All right, and in this case, you have a new policy. So before we've talked about, on policy, off policy. So you have your target policy, your behavior policy. So here's another one. This is called the rollout policy, and the rollout policy has to tell it what to do if you're going to continue to make successive actions from here. In some cases, you may not even have a target or behavior policy. Okay, you just simply know, here's my current state, and this is the policy I'm going to use to play things out. And as it gets rewards and it figures out, which are the better and the worst states from here, it can back those up and basically can say, okay, based on what I've seen so far, after simulating 10,000 different continuations from this state, looks like this particular move is the best move next. So that's a fairly how do I say it? It's a fairly simplistic way of simulating things, because it's just got this one rollout policy and it's just sort of doing it over and over again. And we saw that actually TD learning was much faster than Monte Carlo. So it stands to reason that maybe we don't want to just do this Monte Carlo-like thing where we just play everything out from here. So there's a number of improvements you can make to this rollout, and the one that is sort of, I think, most famous right now has been dubbed Monte Carlo tree search. So there's a number of optimizations that have been applied to this. But the general gist of it, and there's different variants of Monte Carlo tree search, but the general gist is that as you do these simulations, you are starting to form estimates of the value of different actions that you can take, not just from your current position, but from the successor position and the 1-2 way and 3-way, 4-way. And so what you can do is you can use that information to say, I'm no longer going to just use something like the rollout policy forever. I'm going to use that information to direct my simulations towards the most promising looking trajectories. So in Monte Carlo tree search, there's this 4-step process in general. Okay, so I'm going to start out with my current state, and eventually I'm going to build a tree. If I already have a tree, I'm going to do this selection step that says, what is the leaf, the farthest point in the tree that I'm going to pick right now to focus on. A certain percentage of the time, depending on the variant, you are then going to expand the tree. So you're not going to do it every single simulation. That would grow way too fast. But with a certain frequency, you're going to say, I now have reasonably accurate estimates for my small tree, and I'm going to make it a little bit bigger. I'm going to go one step deeper on my selected leaf. We're going to do a bunch of new simulations, update values, and then what we always do is we always back these up in order to get better estimates. And then at that point, we have a slightly bigger tree. We have reasonably estimate value, reasonable estimates, or maybe not. I don't know if reasonable is the right term, but we have our estimates that are gradually improving. And so then we go back to selection again to say, let's pick a new leaf in this tree to expand. So we have a diagram on the next slide. I don't know if this diagram is To me, this diagram is not completely clear, but it is for me better than just me kind of using words trying to describe this. So imagine you've been running Monte Carlo tree search for a little while already, and so you have a tree, because initially it just starts out, with a root. So I've run it a little bit, and I now have a tree of some size. So at the selection phase, the first thing I'm going to do is I'm going to say, oh, okay, well, here's a particular state. I'm going to choose this state and this action here on the left as the part of the tree that I'm going to explore some more. So we expand this and it says, okay, if I take this action, then I'm going to wind up in this new state here. So now my tree's gotten a little bit bigger. Okay. From here, I now need to run a bunch of simulations to say, from here, what is the value of this state, and in particular of these two actions? It's shown as having two actions. So it's going to follow this rollout policy a bunch of times in order to get a somewhat of an estimate for what this is. And then ultimately, once it does that, you're gonna get an estimate for what this state and action pair is. But not only are you gonna get an estimate for this state action pair, but then you can then back that up to the action before it, and then the action before that. And so that's what these red arrows show, is that having run this, let's say, 100 times, I've got an estimate for this, which then refines my estimate for this action, which then refines my estimate for this action, which then refines my estimate for this action. And so what you can see here is, again, the simple rollout algorithm would have just simply said, hey, go and try a bunch of things, try something else, try something. In this case, it's much more deliberate about the kinds of things that it's trying. And so if, for example, in this one set of steps, if we have this new state here and we're looking at these actions, and these red updates said that this action has a very low value, a very poor value, okay, then it is unlikely to get chosen in a future selection step. The selection is probably going to say either over here or somewhere here on the right. That's where we want to do more searching and expand our knowledge of things. If, on the other hand, this had a very high value, then there's a really strong chance that in the next big loop, it's going to actually pick this branch right here and say, hey, let's actually get a little bit more detail. And so I think a couple times we've talked about something like like a queen sacrifice in chess, right? In the short term, that looks like a terrible thing. So you better make sure that you at least look further out and you say, well, what happens if I play things out from there? And Monte Carlo tree search does that. But essentially, this is a very pruned tree. It's not just straight old-fashioned depth-first search. It's certainly not a breadth-first search. It's doing a little bit of a mix. And the mix it's doing is it's prioritizing based on where the most promising looking branches of this tree are. And so if you're doing something like chess, where there's like a time limit, then it says basically at the top, repeat while time remains. So while you still have time, keep thinking and thinking and thinking and go as far as you can. And so that is the famous, at least the basics of Monte Carlo tree search. Any questions? All right. So then that's really what we wanted to cover in terms of how planning is in many ways similar to learning. The difference is that we use simulated interactions instead of using actual interactions with the environment. And as you saw, they can be used in a complementary fashion. And so the Dyna Q algorithm just alternated a step of TD learning with some planning. Instead of doing just very naive planning like we initially showed, where it's randomly picking states and actions, you can go all the way to doing something like a Monte Carlo tree search as your planning step. And then once you've done that, after you take one more action, you can then again do a TD learning step. And then as time allows, you can then do a new Monte Carlo tree search from the new state that you wind up in. So we will see these things if we talk about AlphaGo, we talk about the poker algorithms like Liberatus and Rebel. Okay, so this material then completes part one of the Sutton and Barto book. And one of the things that they wanted to emphasize is that we shouldn't think of the different techniques, dynamic programming, Monte Carlo, TD, we shouldn't think of these as completely separate, independent little methods, but rather think of them as sharing a lot in common and just basically having knobs that you tune on certain dimensions. So all of these estimate value functions. In some cases, we're doing state value functions. In some cases, we're doing state action queue functions. But they're all doing value functions. They all back up values along trajectories. Okay, so whether it's a single step or whether it's a whole episode, you're getting values and then you're using those to update going backwards towards where you started. In the case of planning, it's simulated trajectories instead of real interaction with the environment, but in both cases, it's trajectories. And they all follow the general strategy of, whoops, I missed a word, generalized policy improvement. So GPI, this thing we've talked about, where if you have better value functions, then you can figure out greedily what's a better policy. If you have a better policy, if you change your policy, then you can refresh what is your value function for the new updated policy. So the two key dimensions, and I want to take just kind of a minute on this because it's a cool diagram. The two dimensions that are most interesting for the algorithms we discussed are the width and the depth of the kinds of updates that we're doing. So here's a diagram that's at the very end of part one of the book. And in this diagram, it shows sort of a square space where on the x-axis, left to right, is the width of the update. So on the left is very narrow, and on the right is very wide. And then on the y-axis, this represents the depth of the kinds of updates that we do. And so at the top is very shallow updates, and at the bottom is very deep updates. And if you look at this as a space of different possible algorithms, you have in the four corners, we can actually say what is in those corners. So upper left corner is an update that's not wide. So we're not considering all the possibilities. We're just sampling one possible action. And the depth is very shallow. We're only going one step ahead. If we do that, that is temporal difference learning. That's TD learning. That's Q learning. So we're just sampling one thing and we're going one step ahead. Well, what could we do? Instead of going one step ahead, we could actually go many, many steps, and in fact, all the way to the end of an episode. And so in the lower left corner, this is Monte Carlo methods. So they wait until you get to the very end of the episode before they do updates. We haven't talked about it, but it's covered in the book that there are actually a range of algorithms in between where basically you can do TD learning that instead of going one step, goes two. And then it backs up to the previous two actions that it took. You could go three, you could go four. And so basically along this left-hand edge of this square are a number of TD algorithms that are, instead of just one step, it could be two-step, three-step, n-step TD until if you get to basically infinite step TD, that's the Monte Carlo algorithm, where you go to the end of the episode and then you back up all of the states and actions along the way um, that you saw. So that's the depth um, dimension. So we can also look at the top of this square. So we start with TD where we say it wasn't wide, it was just sampling one thing, and we went one step. If we go the opposite, if we go max width, then this is the dynamic programming algorithm, where we say we consider every single possible action and every single possible successor state from those actions from our starting point, but we're still only going one step ahead. So it's still very shallow, but it's fully wide. Now, if you have a really good, accurate model of your environment, then dynamic programming will give you very accurate values when you do this. So that's wide but shallow. So the other thing you could do is you could go all the way down to the lower right-hand corner. And what if you did wide and deep? Well, that's not a particularly interesting algorithm. That's just exhaustive search. So if you did dynamic programming, but instead of just going one step ahead, you went infinitely deep until you got to every terminal state, that would be exhaustively searching every possibility. And so while that would hypothetically be very accurate, it's not practical for anything other than the smallest, most trivial problems like maybe tic-tac-toe. And you could imagine basically um, a set of algorithms that are sort of in between. Now, the other thing we can talk about is instead of dynamic programming updates on actual interactions, we can now throw in the option to do simulated interactions. And so here's where we would basically have um, um, our DynaQ simple algorithm in the upper right corner, and then you'd have sort of these rollout algorithms that kind of, go deeper, and then ultimately Monte Carlo tree search, if you gave it infinite time, would kind of be down in this lower right corner. But the reality is, we don't have infinite time, so we're just somewhere along this right-hand edge, so to speak. And so that's a way then of thinking about unifying all the different things that we've talked about, not as being, again, having to memorize them as these handcrafted separate techniques, um, but rather just a number of different options you have on these two dimensions. It also turns out that just like you can combine learning with planning, if you look along this TD Monte Carlo um, spectrum, not only is it, for most real world problems, going to be better if you do two-step TD instead of one-step TD. For many problems, three-step will be better, and maybe four. But at some point, like it's not clear whether you should do four, you should do five, you should do six, or um, there's a certain amount of computation overhead, but also just it's not necessarily helpful. But there's another technique that you can do where instead of just picking any one of these, you can actually take a weighted average of one-step TD, two-step TD, three-step TD, four-step TD. You can average them together. And it turns out that there is an approach which has a very reasonable memory and computation footprint, where typically, if you were thinking about this in the Monte Carlo sense, if you were doing, let's say, an average of one step through 10-step TD, you would have to go out 10 steps and then back everything up for the 10 previous actions. And then you could then take the next one and you could go another 10 steps. It turns out that there is an efficient way that you can sort of keep track of all of this and do it all just as an iterative thing, where each time you take one step, you examine the data you've been tracking and you back up all 9 previous actions that you took. And then you take one step and you back up all 9 previous steps with different weights, obviously. And realistically, if you're trying to really have converge to an optimal policy quickly, you're not going to hang out in any one of these corners, but rather you're going to be somewhere in the middle. Monte Carlo search is somewhere in the middle, and people don't necessarily use base Q learning one step. They might use an end step, or even use this technique to blend multiple of these different step amounts into their value function updates. All right, so that basically is our session for today. So what we've done is, again, we did our quick review of how we're formulating these RL problems. And then we differentiated learning using simulated interactions with a model. Planning using simulated interactions from a model versus learning, we're using interactions with the real environment. Looked at the Dyna architecture, and then we talked about different ways we can tweak it, improve it. And then ultimately, we looked at using heuristic and Monte Carlo tree search as ways of directing your planning resources to the most promising state actions in a tree that you kind of grow from your current state. And then the quick wrap up was just to kind of unify dynamic programming, TD learning, Monte Carlo, and a little bit of the planning that we talked about today. So this is hopefully now a foundation for those of you who sort of stuck with us for I think it's been like 6 sessions or something like that. This is really the nuts and bolts that you need for really reading, whatever reinforcement learning papers, with one exception. So we will have at least one more session to talk about policy improvement, which is a completely different approach that does not require you having value functions at all, but rather you model policies a certain way and you actually tweak the policies without actually referencing a state. So it's a very, very completely different way of thinking about things. So that's the one other piece that we'll need in our tool belt, basically, to understand and read current papers. And it's more complex, and but I will say that it seems like a lot of the cutting edge research today in reinforcement learning is in fact using policy gradients, and in particular they're using a combination. So you may hear about actor critic models, and those models actually use both. They use a value function, and so they're using everything that we've talked about, but they're actually combining it with this policy gradient that we'll talk about down the road. So as I said at the very beginning, some of you may have joined late. Next week we have a guest speaker, so it's PySpark. So we'll talk about reinforcement learning again in 2 weeks. But next week it's going to be a fun talk about basically machine learning on Spark. So questions, comments, anybody? All right, well, we're pretty much right at time. We normally, after this, transition to the Q&A, talk about projects and coding. But certainly, if anybody just needs a minute or two to think about questions that they wanted to ask, I'll just pause here and I'll stop sharing my screen and let you guys think for a moment if you have any questions.
Thanks, Ted.
Yeah, you're welcome.
I don't have any